Okay, time to analyze categorical to numeric relationships. So let's talk about the differences with what we just learned in the prior videos. So we're working with this insurance data first. And when we were looking at numeric to numeric relationships like age to charges, we learned the correlation R as our measure of effect size that represents the relationship between age and charges. Now with categorical features, I'm going to point out a couple of things. First of all, we have the term group that is commonly used that indicates the unique values of a categorical feature. So for sex, where in this particular data set we only have male and female, that means we have two groups. Smoker, yes, no, two groups. Region, because there are four unique values, we have four groups. So when you hear the term group, think unique value of a categorical feature. But we're referring to an individual feature. We don't say, well, there are 8 groups in this data set because that's how many there are across all 3 categorical features. No. We won't use we won't refer to groups across all features. We refer to them within a single feature. So there are different tests that we use to look at the relationship between a categorical feature and a numeric label. And that's what I'm indicating here. We'll use either a one-way ANOVA or a t-test. A t-test we use when there's only 2 groups, and ANOVA can be used on 2 or more groups. And then typically we'll use a t-test to look at pairs of groups. So for example, we'll run a one-way ANOVA on the relationship between region and charges, and then we'll run several t-tests to compare pairs of groups within region. So we can use a t-test to compare northwest to northeast, northwest to southeast, and to southeast, and then northeast to southwest, northeast to southeast, and then southwest to southeast. So it'll be a total of 1, 2, 3, 4, 5, 6 comparisons if there's 4 groups. All right, so assumptions of a t-test. You might remember when we were looking at numeric to numeric features, some of the assumptions were things like a normal distribution and no heteroscedasticity. So the assumption of a normal distribution applies with an ANOVA and a t-test once again for each group of the categorical variable, and obviously as well as the numeric label we're comparing it to as well. There does need to be equal variance of the numeric variable for each categorical group. So we still are interested, we still need to, this concept of heteroscedasticity or equal variance across all numeric features applies here with the t-test, but it simply means we're looking at we want to see that the variance or the standard deviation of each group's values of the numeric feature, of the numeric label, have equal variance. And then lastly, the data used to carry out the analyses were sampled independently between groups, meaning, for example, one group doesn't depend on another. So for example, smokers' insurance charges are not a function of non-smokers' insurance charges. Or I guess an example would be if you had actually, let's dive in, and I'll give you some examples as we go along. But there are some other options, just like with correlation. You might remember that if some of the assumptions weren't met, there were other options for different correlation metrics. We have other options for different t-tests if these assumptions aren't met as well. So these aren't hard and fast rules that mean if they're not met, we can't do any analyses. We'll just use slightly different versions. And in this book, we're just going to go through the primary examples of a one-way ANOVA and t-test. And then if you want to look into other options when assumptions aren't met, I've given some links right here. All right, so when comparing 2 groups, the concept is a bit different. We're not going to draw a line of fit through a scatter plot or look at how spread out the dots are like we did with correlations. Instead, we're going to plot a histogram of the numeric label for each value, for each group of the categorical feature. So here, we simply use the categorical feature to divide up the label into 2 groups. And then we look at the mean of each group, and we want to see how far apart the means are, while how spread out each histogram's values are. So when we identify a relationship between a categorical feature and a numeric label, it's based on simply those 2 factors. How far apart are the means, and the further apart they are, the more we can say there's an effect of smoker on insurance charges. If these means were close together, then that means that the cost of insurance charges for smokers and non-smokers were very similar and that there's very little effect of smoking. But they're far apart. Now that's important. However, that's not the only criteria. What if the spread of values for each of these two groups were much wider? For example, what if this purple spread went way out here and crossed over somewhere around there, and the blue spread went way out here and crossed over there? In that case, there's so much crossover of error or variance. There's so much variance in both of these that it's tough to say that those two means are truly that different, since the range of possible values is all over the map. So let me give you another diagram to illustrate that point. All right, here's some better images. So in this first pair of histograms, we have a large significant effect of smoker on label, or in this case on insurance charges. And you can see that the mean here is larger, but the standard deviations, or the variance, is small, and so there's no crossover between these two histograms. There's no crossover between the spread. That gives us a very high t-value and a low p-value. Compare that now to this one, where we have much more crossover between the two. The mean is actually even larger. The difference between means here is even larger than it is here. The difference is there's much more spread or variance on both of these. And so as a result, the t-value goes down and the p-value starts to go up. But this difference is still significant. So as you can see, it doesn't take a whole lot of difference to get a significant effect size of the categorical feature on whatever label. Lastly, the means are a little bit closer. Too much crossover, t-value gets too small. The cutoff is around 1.96 for a significant p-value, and now the p-value here is too large. So we conclude there is no effect of smoker on the label. All right, so the formula is pretty straightforward. It's not something you'll need to memorize for this class, at least not for mine. Check with your instructor to be sure. But right here it says that this t-value statistic is simply the difference between means, and your t-value can be positive or negative depending on which mean you start with. If I start with this one and subtract that one, it'll be positive. If I start that one and subtract this one, it'll be negative. So you can get a negative. The range of t-values is negative infinity to positive infinity. However, a negative just means we happen to take the smaller one first. It's not a big deal. We divide that difference between these means by this variance. How do we calculate or characterize the variance? Well, let's look at the variance of both of them in the original scale. So the variance is the difference between the value and the mean, and that's this standard deviation squared here. That's the variance. We divide that by, or normalize it by, the number of cases in each sample. It could be that there's far more non-smokers in our data set than smokers, so we don't want to overweight smokers in that case. So we divide each of these variances by the number of cases in smokers versus non-smokers. We add that up, and we take the square root of that to get it back in the original standard deviation scale. That kind of cancels out these squared terms here. So it's the difference between means divided by the variance of both groups. Lastly, there's this issue of whether our t-tests are one-sided or two-sided. And what that means is a one-sided test, we ignore the possibility that one mean or one group is likely to be on the right or the left of the other. For example, we have a good theory to tell us that smokers will cost more money. We know that's always true. Therefore, we're not even going to consider the possibility where smokers could be less than non-smokers. And so that means we rule out one of the two tails when we look at the crossover between variants. A two-sided test means we don't have a good theory to explain which one will be higher or lower, and we want to explore it. So in practice, what this means is our p-values are always half the size in a one-sided test as they are in a two-sided test. So again, if I have a good theory to indicate which one's going to be higher, I'll use a one-sided t-test. If not, I'll use two-sided. By default, Python uses two-sided. You have to specify if you want a one-sided. Okay, that's a t-test. The ANOVA is very similar. Now, I know all these formulas look complicated, but they're really not that bad. So the difference here is, rather than just look at the difference between two means, I have to look at the difference between 1, 2, 3 since I have 4 pairs, plus another blue to red, 4, 5, plus another, I missed this one, that's 5, and then 6 between these two. So there's 6 differences I need to include in my numerator, and I get at that right here, the sum of squared between groups. So this means I take the difference between each one of those pairs and square them, which cancels out my negative sign, which means that my resulting f-stat is not ever going to be negative like a t-test is. So I square the differences between each pair of groups. This one minus that, minus that, minus that, and so forth. You get the idea. Then I add those all together, those squared differences. I divide that by the degrees of freedom. What's degrees of freedom? Well, it's the number of groups minus 1. So the more groups I have, the more I want to normalize or divide that sum of squared differences by. So normalize sum of squared between by the number of groups. Sum of squared within, this is our variance in each group. I'm going to take the difference between each mean and the actual value and square those, sum them all up, and then I'm going to divide that by the number of cases, the number of rows minus 1. Sorry, the number of rows n minus the number of groups. So degrees of freedom are just a statistic that allows us to normalize by the number of cases, the number of groups, so that we don't overweight or overemphasize any one of those group histograms. Finally, we simply divide those normalized sums of squared between and within one by the other. Sum of squared between, that's the difference among means, divided by sum of squared within, that's the error, and that gives us an f-stat that ranges from 0 to infinity. F-stats also get p-values, and that will be produced for us by the Python package. So, with that, let's end this. Feel free to take the reading quiz now, but you might check with your instructor to see if it's required or not. If it's required, then you're doing this for points. If not, you can just do it for practice and see if you understand the concepts. But we'll end this conceptual video now and proceed to the next one with how to do all these tests in Python.